So welcome to the MGM course, and we are continuing with the transform model. And I have in the last class I have introduced what is self-attention, and then um, how the input sequence is seen as let us say key, value, and pair. And to create those, transformer uses those weight matrices that takes in the input vectors, and then it transforms them into query vectors, key vectors, and value vectors. And we have seen this computations in the last class, how these weight matrices corresponding to query, key, and value is used to produce these outputs. Then, so this is the idea of scaled self-attention that we saw in detail in the last class. In fact, there is a formula now. There is formula self-attention that takes this Q, K, and V0, and then it gives you the outputs that you want in this case. So the idea behind transformer is that now it uses multiple of these. So let us say in this case we use three of these. Okay, so hence, and each of these attention block, we call it one head, and then we have multiple heads, then we get something called multi-head self-attention. Okay, and this is where we were last time. So what happens, let us say you have let us say the number of let us say the tokens that we have in our sequence. Let us say there are 3 tokens. Okay, so as I discussed in the last class, these tokens could be let us say character by character, or it could be word by word. And we also saw in the case of transformer, the one that was proposed, they also use something called subword, and we have seen this in the last class, how one can create subword tokenization. So assume that, so these are the token at time step 1, time step 2, and time step 3. Okay, so we can stack them together, and this is the length of the vector representation of the token. Okay, so if let us say I'm using word tokenizer, then for a word I will have a vector representation like this as a one row. For the next word I will have a vector representation here as a second row, and so on. Okay, so then we can let us say stack them together. So in this case there are 3 tokens stacked together, and hence we get a matrix of the form xt by d. Okay, so t is the total number of tokens we are considering. Obviously in practice you will have lot more tokens. Okay, and also the dimension d will depend. Okay, what is your vector embedding? Okay, so in the transform model they use I believe 512 dimensions. Okay, so that's the embedding of their tokens. Dimension is 512. Okay, so these are variable. So for this example we take 3, and then d in this case is 12. So we get a matrix of 3 by 12 dimensions. And earlier when we were discussing one head, let us say, then we fed in all these input obviously to one head, and then the dimension of this were such that the output that we will produce will be the key, let us say the query dimensions will be same number of columns, let us say d, as the original one. Okay, that's what we saw in the last class. If you can check again, if we were discussing only one. Okay, so now the fact that we have multiple heads, if we retain the dimensions d, so in other words, if I pick w0q to be, let us say, t by d. Okay, so t by d, or and let us say if I multiply, then maybe I have to take the transpose and so on to multiply it with x, because all this gets multiplied with x. Okay, or I can say, let us say yeah, so the output that I produce is with t, so hence we will say, let us say, t by d, and then it multiplies with the x transpose and so on. Okay, so the point here is that I could have produced these query which were of dimensions which were of dimensions, let us say, t by d itself. Okay, so these were of dimensions t by d itself, but then I choose my wq in such a way that when I apply on this, then it gives me the d dimension is reduced to let us say d by h, where h is the number of heads. So hence you saw that this is now of the wq dimension is picked in such a way that this is now of t by d by h. So h in this case is 3. Okay, so the number of heads is 3. So So I have modified this in a way that output is reduced a little bit, and that is to take into account that I have my multiple heads. I don't want my memory requirements to explode. So each of these, if they maintain D keys, has D columns, space D columns. So all these are like T by D, T by D, T by D. So if you can add up, then you are increasing the memory quite a lot. Okay, as the dimensions, as the heads are increasing. Okay, in the modern day transformers, they use many heads. Okay, so so hence you adjusted that although the input was 12 dimensional, the D was 12, but then now you're reduced to D by H. So 12 by 3 is 4. So these are now 4-dimensional keys, 4-dimensional. This is 4-dimensional. So if I add up the memory, then it is kind of the query. If I add the if I concatenate the 3 of the queries that I get, obviously this query is different from this. So this is T by D by H, and then T by D by H plus T by D by H. Then for the query, I'm still using T by D size. Similarly, I'm using T by D overall. Total combined cumulative size for key is T by D, and then cumulative size for V value is T by D. Okay, so these matrices are chosen in that way. Okay, and so that's the one thing to remember. And the another thing is, as I said, like there are now multiple heads, and the reason behind multiple head is to bring in multiple context. So for instance, I wrote in the last class that where we could have a sentence which has 3 or 4 things in context to be identified. It's like what, where, when, how. Okay, so all this could be. So if I have only one head, then it may be that the expression capability of these head will query only for what. So it will only attend to the questions for what in the sentence, but there could be multiple contexts. So we want to give more expressive power so that the network can also query for where, it can also query for how, when, things like that. Okay, so that's the, let us say, the idea behind that. Okay, so that's how, like, we want to facilitate the model to have more expression ability and to deal with multiple queries within the same sentence. So that's the reasoning given behind multiple head. Okay, so we have this multiple head view. And another thing to remember is that, okay, after doing the self-attention, so this self-attention we have done this separately in the previous class. So from here, if I'm given Q0, K0, V0, what is the meaning of self-attention? We have done that. In fact, we also wrote a formula for how to compute the self-attention. So if I note down that formula again for you, then if you remember in the last class, we wrote this formula: attention Q KV is softmax of Q K transpose by square root of dk and V. In fact, we have derived this formula in the last class. If you can remember, we explicitly did this calculation. We indeed find out that this is how the formula should be. So we have done all these detailed derivations. And so basically this part is when you supply this Q0, K0, V0, and that's the formula for you. You have to supposed to do QK transpose, scale it. So that's why it's called also scaled. So scale by dk. So the current dimension, let us say, for this, maybe it's 4, and then square root of that, and V is the value vector that you have. So there is explicit formula. So we know that there will be output for this. And again, you can check that the output for this, looking at the dimensions of all this, the output for this will be T by D by H. So this head is looking at the input of T by D, and overall, finally, it's producing an output of the form T by D by H. Okay. Similarly, this head H1 is taking T by D input, and then it's producing its own output of dimension T by D by H. And similarly, in this third is the similar one. That's why I have not drawn this. So this is also a third head, and it's also producing T by D by H. Now, if we concatenate that, then overall it will be T by overall. If I see this as a full output, concatenated output, then this is T by D, which is the original input dimension. Okay, and there is a logic behind this, that if I indeed produce outputs which are of similar dimension as this, then it allows me to kind of reuse this. Okay, because reuse this in a recursive way. Okay, so this output again can be fed back into another block of multi-head self-attention, and I may not have to change much because the dimensions were as if I have replaced the input again by the output of this. Okay, so one more scale self-attention I can stack one top of the other. And this is the reason why a transformer is a little bit difficult to understand as first sight. So as if it's like an Inception movie, it's like dream within the dream, and so on, right? So the fact that it builds this multiple levels of hierarchy, in fact, there is one more level of hierarchy. Okay, so the problem in understanding transformer is the hierarchy, not necessarily the algorithm itself. Algorithm is very simple, formula and maths are also very simple. It's just that the hierarchy is the difficult part. Okay, so in this hierarchy, what could be a problematic for you is to understand the dimension. That's why I'm focusing a lot on the dimensions here, is what goes in the dimensions, because when you're coding, you will have to figure out this dimensions itself. Like that's because it's all matrix multiplication. So the only problem you may get is how you divide your data into these dimensions, and then you may get an error that the matrix multiplication is not conforming and things like that. So the most important thing I believe is what are the dimensions of this, and after multiplying what dimension comes out. Okay, so this is why you see the input dimension t by d should give you the output dimension also t by d. Okay, and this is the reason why if we stack it again by another multi-head attention, let us say one more block of this, you will not get into a problem of dimension, because again it will be the recursive application of this. It knows that this dimension goes in and it can produce again same dimension, and then in fact this could be applied multiple times. Okay, but there are like a little bit of more let us say ingredients before we multiply them several times. Okay, so the point here is that the output that I get here, they are stacked for sure, and the idea given behind this is that although so far what is happening in our model is that we have created this, we have taken the input, we have created these query key values for each of these, and they know how to do self-attention among them. Okay, so this process, multi-head attention or the self-attention, is essentially looking into the words at different times time. Okay, so this is one sample, let us say, and this sample has multiple words. So let us say this is a line of 3 words only. Okay, so this 3-line sentence is being looked at each other via this so-called self-attention. Okay, we are not looking any further, right? This, we are only looking into this sample for the moment, and we are looking into various combinations, because this guy, when I'm computing the self-attention, if you can recall, when I'm looking at the self-attentions, then this looks at here key values for here, third key values for here. This is what we did in the last class. Okay, so so it looks into multiple into across key values across the heads. Okay, and that's that is how it kinds of learns the context between different words in a sentence. Okay, so that's why it's called self-attention. Okay, it's trying to learn, it's trying to give attention within the words of a sentence. Okay, so so the idea here is that then what next, right? So it produced this self-attention, let us say some form of embedding that learns has this self-attention. Then the next step is that so far what we have done is that only linear operations are happening. Okay, so basically these are these matrix operations going on, and eventually, yeah, we have attention scores which are softmax and so on, but then we haven't really added non-linearities in the form of neural networks and so on that are very powerful in kind of generating some interesting embedding. So we, as a next step, our goal is that after this, we want to kind of add some certain non-linearities in our model. So so this is what we are going to do next is, so this whole thing that you see here now we plan to pass it through certain non-linearity. Okay, so and let it produce some interesting let us say some hidden representation for our model, which will be used later in the decoding phase. So right now we are only looking into the encoding phase. We are trying to take some inputs and build a good encoder basically, and this encoder will be later used in decoder. So let us say this is sentence of an English word, and this is being represented in encoded form in a nice way, and then we will write a decoder module which will take this nice encoded module and then start decoding or translating the sentence into some other language. So this is the plan that we have. So okay, so this is the kind of the maths behind this, and there is not too much of maths. It's just the hierarchy that you have that can bother you in learning transformers. Okay, so just some remarks on this multi-head attention. So remarks on multi-head attention. So each head operates on a each head operates on smaller dimension d by h, as I said. The overall computation across multiple heads isn't higher than single head attention. Okay, so that's what I explained in the towards the beginning of this lecture. When we were dealing with one head, then we were taking whole of the dimensions, and then we were query each of these query matrices were also of the original dimension at the input. K was also of t by d, and v was also of t by d. But when we thought of having multiple head, we reduced those dimensions. So hence overall memory complexity remains the same, because Q0, size of Q0 plus size of Q1 plus size of Q2 remains T by D, as I explained. So I'm just writing this for formality, and then we can put some more remarks. So the second remark is that each attention heads can run in parallel. Okay, so this is a big deal. Okay, because there is independence in computing head 0 output, head 1 output, head 3 output. Okay, so essentially you can have multiple heads, even let us say 10 heads or something like that. Okay, but then you can compute them simultaneously. Let's say I have a multi-core machines with 10 cores, then each of these I can map them on 10 different cores. Each of the 10 heads, let us say I can map them on 10 different cores, and so essentially I make use of the parallel computing and compute them simultaneously. Okay, so I don't have to wait for computations of each of them one by one. Okay, so that's a big advantage, because modern day architectures are multi-core machines. You often have multi-GPU systems. Even GPUs, within GPUs, you can have multiple threads being combined, okay, to compute on these attention heads. So you may, even in a very large data set case, you can also even go for multi-distributed memory programming, where you have each CPU taking care of this one head computation. So you may use some frameworks like Python MPI, PY, MPI. So you can have this multiple node systems, and then you may do this. You see, even within this, there is a lot of parallelism going on, right? So the computations of WQ, W0, WV are also parallel, because they independently multiply on these vectors. So once you have this map to one CPU, so that CPU may be connected to some GPUs, so that GPU can even make these guys parallel. Even not just that, even multiplying the one matrix with another matrix is also highly parallel operations. So even this itself can be mapped to, if it's large enough, that itself can be nicely mapped to one GPU. This itself can be mapped to another GPU, and so on. Okay, so there are many levels of parallelism you can think of. When I go to self-attention, also I have QK transpose type matrix operations going on. That is also very highly parallel. Okay, and this is one of the reasons why transformer networks are very, very exciting to work with on modern hardware, because there are so much parallelism to be exploited here. Okay, in terms of matrix operations. Okay, so that's a very big plus. Okay, if you compare this to RNN, then you could not have done so much of parallelism, because in RNN one sequence goes in, then output is computed, and then this output is then used in the next step. So you have to wait for the previous output to be computed, so that you can compute the next output, and so on. Okay, but here it's not the case. Here you can do this immediately. You may wonder why I'm not thinking of the sequential nature of the problem, right? So if I am doing things in parallel, then don't I lose the ordering information, or the way one word comes next, and so on. And you are right that so far we have not looked into that, and that will be necessary. Okay, so I will come to that, because the ordering needs to be preserved when we are doing the, let us say for example, translations and so on. Okay, so so that is important. I will come back to that. But for encoder, it's not a problem. Okay, unless you go into some other kind of modeling, like BERT modeling and so on, and you use only encoder type model, then you can use some masking and so on. But then that's a strategy that you can assume. But for the original transformer, for the encoding phase, we let all the words see each other, basically. Okay, give attention, each word gives attention to every other word. Obviously from there it calculates a score that is the most important. So where might attend, the where in the word, where word might attend to restaurant very strongly. Okay, so the attention score will be very high for that, and so on. Okay, so for the moment we don't worry about that. Okay. Also, when doing implementations, there is a possibility that you may want to share the weights across some heads. Okay, there could be a possibility like that. Okay, so although we have not shown this yet, okay, so in practice there is no need to maintain separate set of weights for each head. Okay, so there are multiple ways to interpret this. I may want to share the I may want to share the weights for each head. I may not want to share the head. These are again further modeling assumptions that you may assume. Okay. Okay. So as I have said, that we have discussed this multi-head attention and things are quite clear now until here. The point, as I said in the beginning, is that so far we have not added interesting nonlinearities. By interesting in modern day, it means using some form of neural network. We want these guys to go through some neural networks so that they create some interesting embeddings. Neural networks are very powerful in doing that. So we want to do that as well. So this will be our next step. So then I'm going to rub this and then focus on. So I will take this whole thing as a multi-head attention, and there will be multiple head and so on. And then our next step is that once we have this multi-head attention, we will get certain outputs. Okay, what are we going to do with those next? Okay, so now everything will be denoted as one block, and we call this multi-head attention. And the output we will fetch from that block, and then we will see what to do next in terms of processing. Okay, so hence I'm going to rub this now. Okay, so continuing, now I will previously I showed you multi-head attention. Now I will just represent that as one block in the encoder block. So I'm going to draw this again, but so just to remind you, so that we have at the bottom we have source, or we call it input. And usually for transformers it's subwords. So for instance, where can I find A and then pi. So we have seen this in the last class. So pi and then z. So these are the subwords, right? Area. Okay, so you can see this how we created the subwords. So this is the subword. So given a sentence, we have broken them into subwords. So now each of them will have their own embeddings. So that goes into the next step, like that. And then we call them, let us say, x1, the embedding for where, x2, embedding for can, x3, embedding for I, and x4, similarly x5, and we can keep it general. Let us say xi are the number of inputs. Now, to map from what the way we have written in the previous multi-head attention is that we stack them like that. Okay, just to be sure that you don't get lost. Xi. So this was our t, but now there are I of them. So this is I, and this dimension, let us say each of them are d dimensional. So previously we wrote t by d, now it's like I by d, but then I don't stack them one below the other. I just now write them x1, x2, x3, x4, x5. Okay, so I hope you don't get confused. Okay, so these are the input embeddings. Okay, so I did embedding in some way. Okay, again, how we do this can be different depending on what method you use, but you have to translate them into some vector basically. Okay, so then we have this encoder block. So we have so transformers are also encoder decoder model. Okay, so this we are dealing with is encoder. So we saw this in the beginning in the previous class, and then we have let's say, so this is our encoder block. Okay, so this is our encoder block, and there will be a decoder block here as well. Okay, so we will come to that. So the whole multi-head attention that I showed you in the previous class, previous discussion, we had like 3 heads. Now all those will be combined into one block here, and I call it multi-head attention. Multi-head attention. Okay, so everything is now encapsulated into this one block. Okay, so and then we know that the output of these was of the same dimension as the input. So in this you can visualize there was head 1, head 2, head 3, 4. They had their outputs column was d by h, d by h, d by h, but then there are h of these. So d by h times h becomes d. So they become the same dimensions as input, and the time was also the same. If I stack them x1, x2, x3, x4, so it will be like I by d output again, as same as the input. Okay, so we have just made it into just one small block now. Now we are thinking, what are we supposed to do for the output of this guy? Okay, so if the so as I said, for expressions of our model, we always now use some form of neural network, because neural networks have very powerful expression capabilities. So it's used almost everywhere now. So it makes sense to let it pass through some feed-forward neural network that we have seen in the previous classes. So then we say that it should have, let us say, a feed-forward neural network. Okay. So what we expect is that we have a and one more, I mean, like few more things I should point out for the original transformer is the original transformer embedding dimensions was in the original transformer. So what do I mean by original transformer? This is the paper, attention is all you need, right? That's the original one. Okay, that we call it original. Attention is all you need paper. Okay, in the original transformer, they say that the d, okay, so we are looking at t by d, or in this case let us say I by d. So they say the d, the vector embedding, so where go is represented by vector. Okay, so they say that this vector embedding dimension is 512. So the embedding dimension they choose is 512. So meaning where is represented by vector x1, and x1 is a 512 dimensional vector. Similarly, x2 is 512 dimensional vector. The dimension does not get changed because some words are small or some words are big, obviously. Okay, so each word are well represented. Even this pi or this zz, which is not necessarily a known word, but we can always give it some representation as a vector, and it should be unique, obviously. So each word should have their unique vector representations. So this is what it means. So each of these x1, x2 up to xi are 512 dimensional vectors. Okay, and the number of heads that was chosen in the original paper or was 8. Okay, so in the original, so this let us say we call this point 1. A point 2 is number of heads, attention heads, was at 8, right? So in our case, then it says that h is 8. So d by h, right? So our d by h will be 512 divided by 8. So this implies d by h is 512 divided by 8 is, I believe, 64. Okay. So what does this mean from what we have understood? So this means that there are 8 heads, right? So this means that this multi-head attention block, it has 8 heads, right? So 1, 2, 3, 4, 5, 6, 7, 8. So this is head 0, this is head 1, head 2, head 3, head 4, head 5, head 6, head 7. Because it starts from 0, so total is 8. And then it is saying that the d by h is 64, right? So the number of sequence in our case is I. So each of these is the output that will be produced by each of these will be I times d by h, which is in this case is 64. This also produces I by 64, and so on, I by 64, according to what we have seen before. So if I combine the, let us say, one of the query matrices, and then the total is 64 times 8, which gives me the output of the query vectors. Total query vectors that I will get will be once again 512 columns will be there in the output of the query of the head 0. Okay, so the total output that will come, that the combined query vector, if I stack them one after the other, then obviously, I mean, I should correct a little bit, because all this computation of query key value, so there will be query key value for this, query key value for this, query key value for this, and then you go for self attention, right? So you compute self attention for that, and then you combine them together, you stack them together. So final output is indeed I by 64, I by 64. So if I concatenate them, then total is I by 512. this is the output that's coming from this after doing the skew, self-attention, and whatever we have seen, okay, with an example of the 3 heads. And this is the same dimension as your input. This was also I by 512, okay. So this is what it means here. So let us say we understood this. So now I go back to the original diagram where I had this self-attention. Just I wrote this. So this is our multi-head self-attention, okay. So this is our multi-head self-attention block. And then going forward with our proposal is that this output, which is I by 512, is supposed to pass through some nonlinearity, interesting nonlinearity. So in modern day, interesting nonlinearities are neural networks. So now our focus goes into neural network, okay. So also, as I said before, on all the operations that we do here is now parallel. Each computations of this multi-head for 8, in our case the heads are 8. So in fact, on a course level, even you can have the 8 levels of parallelism, and within that, when I'm computing query key values, also I have 3 ways of parallelism. Within that itself, when I'm multiplying with this query matrices for the input, again that's matrix and matrix operations, again there is further level of parallelism. So I have already explained all this. So there is a lot of parallelism there, okay. So that's the second point. Relating any input, relating any 2 inputs, it could be even long distance one, is order 1, okay. So what does that mean is that in multi-head attention we have these multiple heads, and then within that we have query key values for each of these heads, and within that we do look across all the inputs, okay. So there is a direct attention given to any input, okay. Now how much big attention is given or small attention is given, that will be determined by the attention score that is calculated here, but we do give that facility to the model that you are allowed to look directly into all the inputs. This is unlike RNN, because in RNN, if I'm computing for x6, then it's only able to look at the output that came from x5 or the hidden representation that was produced at t equals to 5, which will be in this case, let us say h5, okay. And then x6 I have to compute, then it's only able to look at x5. x7 if I'm computing, then it's looking at the hidden representation of h6 if I'm trying to produce at at 7 time step, okay, 7th time step. So these are the differences, okay. So in other words, if I'm computing x5, okay, a hidden representation for h5 which will be produced as h5, then I am only looking into h4, but then I'm not looking directly into x1. To look into x1, I have multiple steps to follow. So it depends on this, and then it depends on this x2, and then it depends on x1. So there is order of like 4 steps back. It has to it has only direct, it can only directly look at x4, but not directly at x1. But here we allow them to look directly. So this is like order 1 access to the inputs, okay, any of the inputs, okay. So this is one also another advantage of that. So one of the things is then, okay, so if I indeed have to maintain an ordering, let us say for some reason, let us say if I want to do that, then how should I proceed with let us say if I have to indeed preserve some ordering, okay. So because RNN could do that, but here we don't have the ordering concept here, because each of these is looked into each of these without having regard to the ordering, okay. So is there a way to encode ordering also in these inputs, okay. So this is also an interesting addition to this because then there is a concept of something called positional encoding. So that says that I will give some additional let us say positional encoding to this, okay, so that I can distinguish between what is before and what is after, okay. And this itself will be a form of vector operations, okay. So let us see what this positional encoding mean, okay. So when using transformer, we lost something in the process, and that is the ordering of the word is lost. Ordering of the word is lost, okay. And we are dealing with time series data, and we so far there is no concept of ordering that we give to the transformer, okay. So So if we look into RNN, so with recurrence, um, so for example in RNN, the fact that we processed inputs in order or sequentially automatically gave sequential context. Okay, so this was inbuilt in RNN, that I fed one input and then I fed another input, so ordering was maintained anyway. Okay, but here we are throwing everything in one shot. Okay, so when we look into self-attention, then self-attention operates on sets rather than on ordered elements. So in sets, as we know, there is no concept of ordering in sets. I can put any element in the set. The ordering concept is not needed there. Okay, so basically we can think of these as sets. Okay, here we did not specifically look into the ordering. Okay, so when word order changes, we want to preserve that ordering. Okay, so when word order changes, we want to preserve that order. Okay, so we do because when the order changes, the meaning also changes. So that may not be possible in the current framework if indeed we are working with like multiple ordering changes in the words and so on. So in this, it becomes essential that we maintain the ordering of these sequences. But again, once again, if we do maintain the ordering and we only resort to just giving one input at a time, then again parallelism will be lost. Okay, so hence the authors came up with very nice interesting idea, is that they introduced something called positional encoding. Okay, and this encoding maintains this order, and this is just a vector addition operations. Okay, so there is no explicit ordering being maintained. It's just that the values of this guy will somehow be encoded in a way that it's less than the value of this guy and so on. Okay, so this will be maintained in that way. Okay, rather than we saying that let me put this vector, after that let me put this vector, after that let me put this vector, which is done in RNN. Now what is interesting now is exploited in transformer, which I believe is a very interesting idea, is that change the entries of these inputs encodings. They are already vectors, but change their inputs in a way that they the entry wise they are less than this guy is less than this guy is less than this, and things like that. Okay, so that way you know that they have certain ordering. At least the model will try to understand that. Okay, that there is a relationship like that. Okay, so then how do we do that, right? So then the next question is, how do we maintain that ordering? Okay, so essentially which type of vectors I'm going to add to these guys so that I maintain the ordering between them. Okay, so or let us say pointwise ordering, because in general in R2 there is no concept of ordering. So if these vectors are in R2 itself, so the ordering concept only is in R in general. So in R I can say that A is less than B. Okay, so the ordering works in R, but as soon as I go in R2, then there is no concept of ordering as such. Of course we may define certain ordering depending on what we have. So how should I say, like this number is less than this number, okay, or this number is greater than this number. So there is no ordering in R2. So obviously like you may define your ordering. So you may say that let me do it component wise. So let me check first, let us say I go for alphabetic ordering. So I will first look for the first component. If it is less, then the vector is lesser than this. If they match, then I will look at the second component. If the second component y is less than that, then I will define that the whole vector is less. Okay, there may be ambiguities and so on. I'm not looking into that, but so so here we are even looking into 512 dimensional vectors, and natural question is like, how do I say that one vector is less than the other? Okay, so the paper introduces a concept of positional encoding. So we will see how it creates the ordering. So I will come back to this non-linearity before, later on. I said that I want to introduce a neural network here, but even before going there, I thought that okay, let us discuss whether we can provide some context of ordering to this input. Okay, so this is where we will try to introduce the so-called positional embeddings. So the positional embedding concept is as follows. So the paper proposes the following. Is positional embedding POS to I, it will be sine of POS divided by 4 zeros to I divided by D model. Remember, D model in our case is 512. Okay, they call it model size 512 because it remains 512 throughout, right? So multi-head attention also produces 512 after concatenation and so on, right? So that's called D model, and then PE POS of 2I plus 1 is cosine of POS, and then 1, 2, 3, 4 zeros, and then 2I plus 1 divided by D model. Okay, so the way, so right now it's just a formula, and the question is how will be the embedding happening for these vectors x1, x2, x3, x4, and so on. So the way it does is that it takes a vector x, and so let us say in our example, let us say it's just 4-dimensional, and then it adds this positional embedding for x1. So this is positional embedding for x1. This will be 1, 2, 3, 4. So basically, component wise, it adds some positional embedding. Now the question is what is being added, because x1 we already know, but what is being added here? So this is based on this formula. Okay, so it looks into the POS. So this is position 1 because this is the first word in the sequence. So the POS will be 1, and then it looks into the component. Okay, so let us say this is the odd one. So I equals to 0. So I equals to 0. I mean, if I have to produce 1, then I will take I equals to 0. Then it will be 1, 1. Okay, so if I have to compute this quantity, so let us say this this is like small p1, small p2, small p3, small p4. Okay, let us say this vector, and let us say this is for position 1. Okay, so we denote it like this. Let us say, so for the first vector in the sequence x1, we want to compute positional encoding for each of the components. So then p11 will be let us say from here p11, this means pe. So this is for the odd, and this is for the even positions, right? So for odd positions, since I'm looking at p1, so if it's odd position, then the 1 will be produced by I equal to 0. So if I is 0, then I get the 1, and then position is 1 because that's the first entry in the sequence. So then it will be pe1, I is 0, so this overall is 1. So this gives me pe11, and that will be given by the cosine of 1 by, and then I is 0, so this is 1 by D model is 512. Okay, in the original paper, D model was 512. So this will give you some number. Okay, cosine of 1 by 10,000, and then you take the root of that. Okay, so this gives you certain number, and then if I look into p12, so if I look into p12, then I have to use the even one because it's a 2. So then I will be 1 here in this case. Okay, so this, but then I have to look into the even formula. Okay, not the odd formula. Okay, so if your I equals to 1, then we have, and this is still the position is 1. So this is cosine of POS is 1 divided by, and then 2I, and then so this is sine. Sorry, so this is sine now, and then so 2I, in place of 2I we have 2. So this is 2 divided by 512. Okay, so this way it creates this this entries for the positional embedding, and for odd and even it uses sine. For odd it uses cosine, and even it uses sine. So if I have to compute it for x2, then the POS will change the post will be position will be 2, and then again I will look at the even odd, and based on that it will give me positional embeddings. Okay, so it will be good to kind of play with this in a Python code and see for yourself what are these values, and if you plot them, let us say you pick x1, x2, x3, some vectors you may take, and then see what happens if I add those, if you add those positional embeddings and then plot it for yourself and see. Okay, but this is what it is, and then what will be the effect. So I can show you some plot that I a sketch of a plot. So after positional embeddings, so what might happen is that this so this is, let us say, dimension 1, and this is like dimension 2, dimension 3, and dimension 4. By dimension we mean the x values, the first entry of the x value, second entry of the x value, third entry of the x value. Okay, so here so if I add the positional embedding, so let us say this is our positional embedding PE, and this is the positional embedding for x1, and these guys get multiplied component wise, and component wise when they get multiplied, so not multiplied but added, then I will see them as, so let us say this is some sine, this is some cosine. So for each of these I have these positional embeddings which are here. So as you can see, for position x1 I have this these vectors which are here lining vertically at this position. But if I look at the second position, which is for x2, then you will see that these are have positional these have positional embeddings after x1. Okay, and that is the reason why there is this ordering being seen here. Okay, we have created this this ordering. Okay, so these components are lesser than these components, are lesser than these components, and this is the reason why we get this ordering. Okay, so this positional encoding vector is given for each of these vectors, and they are added. So there is a positional encoding for x1, for x2, and x3. So they will be added for each of these. So there will be a so I can. So so I can make a little bit of space here. So for the positional encoding, so let us say this is our encoder block, and then this goes like this. But then here, let me check what is the, yeah, so we use a notation, let's say plus. So here we have plus notation, and here the positional encodings are added. So these are the positional encoding calculation that we did. We will do positional encoding for x1, then x2, and x3, and x4, x5, and this creates this ordering that that we wanted to have in the sequence, in the input sequence. Okay, so that can be done. And okay, so so we have this positional encoding, and then we know that there is a multi-head attention block going on here. So this is multi-head self attention. Okay, so this is the multi-head self attention block that we wrote before, and now the multi-head self attention is taking these vectors and has certain ordering information also going in. Okay, and we did not break the parallelism. Okay, we just encoded the ordering as a vector representations, that one vector positional encoding is less than the other positional encoding, and so on. Okay, so that can be done, and there is no loss of parallelism here. Okay, and then the next step, I come back to what I was saying a lot about that it should go through some non-linearity. Okay, so there is still no non-linearity. Okay, so there is still no non-linearity. Okay, except for the softmax, which is just like calculating the attention score and so on, that goes in here, but there is really no non-linearity for the output that is being produced here. Okay, so we want to do that. We want to bring some from non-linearity, and in our case it will be a form of a neural network. And the so if we do that, then basically what we are looking for is a a neural network that goes in here. So as we have seen in the neural network lecture, we have neural networks which could be represented as a graph like that, and then so we can think of a fully connected, and then they are, so this is a feed forward neural network that we are talking about. So feed forward neural network. So we want to bring in a nonlinearity. Okay. So obviously the input layer, as you recall, the way I have written neural network is now bottom to up. Okay. But earlier the way I represented neural network was left to right. So these are both ways people write this. Okay. So earlier the way I introduced is that input is like this. Okay. So there is no edge between each other. Okay. And then like that. Okay. So I have represented a neural network like that. There's an input layer, then first hidden layer, second hidden layer, then output layer, let's say. But here because I'm going this way, the input will be fed this way. So this is my input layer, and then this is the first hidden layer, second layer. So it depends how many layer I want, how deep I want my neural network to be. So that's my neural network. Okay. And this is the nonlinearity, a very powerful one that I bring in here. And obviously, what would be the size of the input layer, right? It should be matching the output from here. As I told you before, the output of this will be the multi-head attention output that it gives us is the same as the output, the dimensions that it took as an input, which was I times 512 in this case. Okay. So then the input. So the way it is that what we have as an output from here is I by. So I is the number of rows and 512 is the number of columns. Okay. So this is how we have the output stacked like that. But when it goes to the neural network, then it will work on one row at a time. Okay. So one row will go. So that's 512 dimensional vector, and then some value is created. Okay. And then another row will go, and then another value will be created. Okay. So it will go in a step by step like this. Okay. But I'm saying step by step, but again there is a parallelism here as well. Okay. So let me explain this here. So I have a neural network. Okay. So we have neural networks. Okay. So I'm drawing some arbitrary graphs. Okay. So this is our neural network, and it takes the vector like this. So there is I by 512. So these are the I inputs. So what it takes is that these are the inputs, and these inputs are 512 length. So this input dimension should be 512, obviously. And so one possibility is that you feed it one row, and then it produces one output, let us say. Okay. And let us say this output also we want to keep it as the same dimension as the original. Okay. Because there is a concept of stacking once again. As I said, building transformer is like the Inception movie. You have dream within the dream within the dream. So that's how things will be. This will be multiplied again. Okay. So this is why it makes sense to keep the output after the neural network processing again I by 512, and this is what is being done here. So hence we want this 512 input vector to come out as a 512, let us say, output vector. Similarly, the second one goes in and it comes out as 512, and similarly again we will have, let us say, I by 512 output. So there was no reason again to process these one by one. So I can have this neural network processing each of these inputs, let us say, even parallelly also. It's possible to do that. Okay. So we may try to do that as well. Or yeah, so again there will be a question of whether I want to keep the weight shared or I don't want to keep the weight shared. So there will be a choice again here, but there could be a possibility that we do some of these in parallel. Okay. So so we do this, we let it go through this nonlinearity, and we, as I said, we try to maintain that the final output that comes out is again I divided by 512, I times 512. Okay. So from the neural network I can say that, let us say, the outputs that I get, so either sometimes I look it like first input stacked below second input and third input, but then sometimes I also write like this, x1, x2, x3, x4. So if I use this notation, then the outputs that I will get will be h1, h2, h3, hi. Okay. And each of these h are same dimension as xi, and in the original paper each xi's were 512 dimensional, and here also we maintain that h1 hi's are also h1 h2 up to hi are also, each of them are 512 dimensional. So, and again, why is that? Because we want to stack these guys again. Okay, so that's the idea behind transformers, is we will stack them again. So there is multiple level of hierarchy, as I said, because there was self attention, but then we had multiple heads. So that's the hierarchy that we build, multiple heads. Now we added nonlinearity and make sure that the input dimension is the same. Okay, and between that we also added positional encoding to preserve the ordering. But then the next stage we will say, now stack them multiple times. So in the original paper they will stack it 6 times. So if you recall, this is an encoder block. Okay, so this is an encoder block we have, and this encoder block together will be stacked 6 times on top of each other. Okay, the very fact that the outputs of each of these are same each time, it should not be a problem in terms of dimensions and so on. Okay, so that's the idea. So as I said, in the original encoder in the original paper, this is like 6 times. So in original paper, so I may now remove this. So in original paper, there are 6 encoder blocks. Okay, 6 encoder blocks are there, meaning these guys will be stacked 6 times. That's why. So this, not this, I mean 6x means for the whole block. Okay, not the neural network, but this whole block is stacked on top of each other 6 times. Okay, that's the another level of hierarchy. Okay, so what happens if we do stack 6 times? Okay, so there will be some issues if we stack 6 times. Few of the issues will be here. The first one could understand the positional encoding, but if I stack it one on top of the other, will it remember that there was a positional encoding to be considered? Okay, so that this could be one of the things. And then the very fact that we stack them together, will there be information loss? Just like we have in RNNs, we have multiple of these time steps, and then processing that happens one after the other. So will we lose while doing the back propagation to compute the gradients, will there be similar issues as vanishing gradients if I kind of stack them one after the other? Okay, so these are the issues that we face. So to look into those issues, then next set of ideas will be employed. So what we want to do as a next step is that we will have a so we will have a 6 of these encoder blocks, but within this again there will be some modifications that is proposed in the paper, is that while we go through these multiple layers of hierarchy via neural network, we will lose certain informations along the way. Okay, so then the paper proposes that these encoder blocks also needs to be modified a little bit in the sense that they don't basically for stability of not leading to vanishing gradient stuff like that. Okay, because there is also like deep neural network here going on here, so there may be some issues with vanishing gradient and so on. So this encoder block itself is modified further, and this is what we will see in the next step. So so we will build further on this and see what are the changes we are supposed to do. Okay, so the original proposal that in the original paper, what happens here is that if I reuse this, then so as I have written, it is 6 times. So what I want to do is okay, there is indeed a positional embedding, so I can write this in short, positional embedding going on. So what in original paper it happens is that these multi-head attention processed by neural network, this we can call it one encoder block. Okay, so this is encoder, and this is like 6 times. Okay, so I'm just like kind of redoing this, and let us say this is the 6th one. Okay, so these are like encoder block. Okay, so what happens is that the input goes in, positional embedding goes in, and the encoder block has multi-head self-attentions, and then processing by a neural network, and then the information flows into the another next encoder block, and then again it has its own multi-head attention. Okay, so these are 6 of these, right? 6 of these, and then it goes through the neural network processing, and then it produces same dimension output. That's how what we maintain, and again it has own multi-head attention block, and then and so on. Okay, so it does it, let us say, 6 times. So in the original paper, what they observe is that when they do stack this, then there is a problem that in the original idea that we just have these neural networks and then pass it through, then there are certain issues, and these are like, for instance, I can write it here. So some of the issues that we have is that shifting inputs from earlier encoder adds noise. Okay, and depth leads to, so if we have multiple of these, then the depth leads to earlier information being forgotten. And also issues of vanishing gradient, vanishing or even exploding gradients. So these are the issues that we have also seen in RNN. We have a long sequence network, then long chain network. Then obviously when we do backprop, I have also discussed about that. Then there are issues like vanishing gradient and exploding gradient, and also the information getting lost. So if we indeed do like this, then there is a possibility that we lose the informations as we gradually go. And you may say, why I'm doing that? Like, well, we want to increase the expressibility of these blocks so that they can learn complicated pattern, so that we want to give them another encoder block. So that's a way to kind of provide more expression ability, because this guy also has a neural network and this guy has and so on. Okay, so that's the reason why we want to do that. But at the same time, we also want to make sure that gradient flows in a good way, they don't vanish and things like that. Okay, so then the original each encoder block is modified a little bit so that it produces an output which is relevant for the next encoder block. Okay, so then we will go back to again to the encoder block, and then we will add some neural network tricks, which is also used in other set of architectures. Okay, things like batch normalization, and then things like skip connections. So these are some tricks to make the learning process more stable, or like prevent things like vanishing gradient and so on. So let us now include those neural network tricks that we have. So, and then I'll also make a space here so that I can include those tricks here. So let us say I have this, and then I have positional encoding that goes here, and then I have this encoder block, and within the encoder block, then I will I have this is one encoder block, and then we can stack them obviously, as I said. So we have multi-head attention, and then what it does in the paper is that you add something called add skip plus layer normalization. Okay, so here we add, I will explain this, add skip plus layer normalization. Okay, so this is being added to make it more stable. Okay, so let us see what is this. These two things are skip plus layer normalization. This is done before using the neural network. Remember that we have wanted to use neural network, but to make it stable, we added the skip and layer normalization. So let us first look into let us say layer normalization. So layer normalization, but before layer normalization, so first let us look into something called batch normalization. So in a batch normalization in a neural network, what happens is that I have a neural network. Now I will show left to right. Okay, so this is my neural network. Okay, so this is my neural network, and so we know that a neural network can process a batch of samples, right? So let us say my sample, your first sample is x1, then my second sample is x2, my third sample is xb. Let us say the b is the batch size. Then I can pass these samples one after the other. So if I pass these samples one after the other, then I will get, let us say there are 3 of these, and then what I will get as an output for first sample is the first hidden layer, second, third, and fourth. I mean only 3, I guess. Yeah. So there are 3 in the batch. So for each x1, I have output this. This is let us say some h1. This is some h2. This is some h3. Okay. So let us say 3 of these. Okay. And the batch normalization idea is like it says that so you have some outputs. Let us say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So let us say we produce some outputs. Then the idea here is that you do a batch normalization. The batch normalization means that you compute the mean across the batches. So compute means. So basically, let me say this is like mu1 across this, and then this mean of this is mu2, mean of this is mu3, mean of this is mu4. So basically, in this case, what is happening is that I will wait for the 3 outputs to come. So the output from sample 1 is h1, sample 2 is h2. So basically, the whole batch output I will wait, and then once I have the outputs from 3 samples, so the batch size is 3, let's say, then I will compute the mean across the component of first component, across the second component, across third component, and then I will modify the output by subtracting the mean from each of these. Okay. So basically, this is called mean normalization of a data. Okay. So given a data, if I subtract the mean from the data, then it's called mean normalization. Okay, and I can also divide by the standard deviation. So the way the normalization of data happens, the mean normalization happens, is that we have this mean computed, and then what we compute is x hat, which is x minus mu by sigma. Okay, and then mu is computed from there. Okay, and we do the subtraction of the mean from there, and then we divide by the sigma. So in this case, again, sigma will be computed as a xi minus mu. This is the formula for sigma, and then so this is how we compute the sigma, and we will put that sigma here. Okay, and then we will subtract the mean across this, and then we compute the sigma here, and then we subtract the mean, divide by the standard deviation, subtract the mean, divide by the standard deviation, and then each of these vectors now get mean normalized, let us say. So this becomes mean normalized, this becomes mean normalized, this becomes mean normalized, each of them. So this is called batch normalization. Okay, and then but what a transformer introduces is something called layer normalization. So it's basically normalizes across the layer. Okay, so the reasoning given is that I don't want to wait for all the outputs coming from the batch. Immediately, if I have a data and then I have layer wise data available, then I will kind of do the mean normalization across the layer. Okay, so the way that the transformer does is so-called layer normalization. Okay, so in layer normalization, if the output is like this, then it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then in this case the mean is computed across the layer. Okay, so that's the difference. Okay, so here I'm not waiting, let's say, for all the batches that I need to, because for batch normalization I'm computing mean this way, but now I'm computing this way. So I will compute the mean, subtract the mean, and divide by the sigma for this layer. Okay, and similarly I can do it for this layer and then this layer. Okay, so this is called layer normalization. This is mu1, then this is mu2, and this is mu3, and then you do the same way. Okay, so the x hat that you will compute, the outputs you will modify by the corresponding x hat, which will be the mean normalized by sigma, and then sigma will be square root of 1 by dh. So this dh is the length of the layer, basically the depth of the layer, basically. So then the usual formula, like xi minus mu I mu squared. Okay, so I equal 1 to dh. The dh is this size. Okay, so this is what is mean normalization. I computed the mean, and then it will be 2 minus mu, 5 minus mu, 8 minus mu, 11 minus mu, square of that, sum that, and divided by dh is 1, 2, 3, 4. So it will be 1 by 4. So that will give me sigma. And then I do this, the whole vector x, basically minus mu that I computed, and then so whole vector minus mu1. So component wise 2 minus mu1, 5 minus mu1, 8 minus mu1, 11 minus mu1, and divided by the sigma for this layer. And this output is now modified by, replaced by x hat. So that will be the normalized variant of this this layer output. Okay. Similarly, there will be normalized variant of this layer output, and this we call it layer normalization. Okay. So this is what is used in the transformer. Rather than batch normalization, it uses something called layer normalization. Okay. So this is one of the ways to stabilize your network. Okay. This usually helps. Okay. So one may kind of look into the proof mathematical details of how this may stabilize, but usually like certain kind of normalizations of vector usually helps usually helps, right? So in this way, you may look into the original paper and then see if there is a proof for stability and so on with this. Okay. So but this is usually done in practice. In fact, you may do this right in the data itself. Usually sometimes in the input data itself, you may do some form of mean normalization and so on. Okay. If the data has a lot of variations going on, then it's good to kind of numerically, to make it good, it's good to normalize data like that. So this is what we have covered so far, is this layer normalization that is done, and this is obviously applies to the neural network that we that we have. And then we have so-called skip connections. Okay. So a skip connection is another idea that is used to stabilize a neural network. So let us see it here. And in the skip connection, what we do is, again, it's an idea for the neural network itself. The idea behind skip connection is that if you have a deep neural network, then there is a possibility that the informations that we have from the previous hidden layer may not be carried well in the forward layer. So then what you do is that you provide the information that you have in some layer previously to the future layer as a form of input. Okay. And that's why it's called skip. Because then you skip some hidden layers and provide the input in the future layers. Okay. So that's the idea behind skip connection. So what it does in this is the following. So I have layer I, and then I have layer J, and then input, and then layer K, and here the output from here is fed to here. Okay. So this is the idea behind skip connection. You are at the layer I of your neural network. It produces some output X. This output X is fed directly into layer K. So it skips some layer in between. Okay. The idea behind is that the output that was produced at layer I may be lost if it goes through layer J for some reason, let us say by vanishing gradient, okay, or exploding gradient or things like that. So usually in deep neural network community, they have found that in some problems, adding these skip connection helps. Okay, in the stability of the network, in carrying the information in a good way to future layers. So this is a very simple idea about skip connection. So in the layer normalization, just to add a little bit, when we compute this, then this normalized weights, then there is sometimes also a way to have some learnable parameters x hat plus beta, where gamma and beta are learnable. Okay. So after doing this layer normalization, they add these gamma and beta also as weights of the network. Okay. And so this is the good thing about supervised learning. Okay. If you're not very sure, then maybe put a weight after normalization. Maybe after normalization something was missing. So let's say I put some gamma and beta as well, and let the network scale after the layer normalization. Let the network scale it properly again, so that it gets a better Z that can be used later on. Okay. So in some papers they use that as well. Okay. So we have this skip connections, and then we have, so basically in words, what skip connection does is that, so the skip connection method, what it does is that takes output of layer I and adds it to output of layer J. So takes output of layer I and adds it to the output of layer J, and that's what we did here. Okay. So just I wrote it in words. So what are the advantages of skip connections? So advantages of skip connections are during forward propagation, it reduces the chances of losing. It reduces the chances of losing signal from earlier layers. Okay, that's what I also explained in words a few moments ago, and it also allows, let us say, during back propagation, it also allows. So maybe I can write it here. So the second argument behind this is that during back propagation, it allows gradient to flow, to keep flowing. Okay, so that's a better way to keep flowing on skip or residual connections. Sometimes it's also called residual connections. Okay, so I have written this in words for completeness, that this is the reason behind we use skip connections. And so with this, then we can have this diagram. We can complete this. So basically, there are skip connections and layer normalizations, and this is all part of the feed-forward neural network. And then so this yeah. So and then we have, so basically we can replace this with feed forward neural network, and then we have a skip connections added plus layer normalizations added. Okay, so let us say this. So these are the modifications that we will do after we get the data from multi-head attention. We do pass through nonlinearity, but we have this skip connections plus layer normalizations that is being added in the neural network itself, and we may do this also as a post-processing step. Again, we may do one more step of, let us say, layer normalization and so on. Okay, so and then we provide the data finally to this, and then one more is yeah. So one skip connection also goes from here basically. So rather than getting only output from the multi-head attention, before multi-head attention, the data is also fed to the skip connection here. Okay, so that it also has a view of what was the input data, and also the data that comes from multi-head attention. So there is a skip here as well, and then also in the original paper there is a so this is the this is how the encoder block looks like, and we have basically 6 of these stacked on top of other, and we have added skip connections and layer normalizations as well. And if we look into some variations of this, then which is more stable than the original paper, then I'm going to do that. The variations that some of the papers have now is that they have a layer normalizations before, then they have multi-head attention, then we have further layer normalization here, and then we have a feed-forward neural network. And then the way it is done is that there is a skip connection from here to layer normalization here, and then there is a skip connection from here to the output that goes here. Okay, and then finally, obviously, we have an output. Let us say these are h1, h2, ... hi. So the modern variant tries to use this, which is more considered more stable, that they do the layer normalizations, then followed by multi-head, but then the input that goes before layer normalization goes here. So these two are skipped. So it's not that the output from here is skipped. So this output is also taken, but this output is also taken, and then it goes through some layer normalization here, and then the output that was produced here is also fed directly here, and then it goes through layer normalizations, and then some feed forward, and so on. Okay. So this is the idea behind the encoder, and we have 6 of these. Okay, so we have 6 of these stacked on top of each other, and so continuing with this, we have a little bit left. We have a little bit of the decoder left, but decoder also is very similar to encoder. So what we will do now is we will look into the decoder also now, but there are some remarks that I will write down first. So some remarks. So for the for encoder, it is okay to have each output to be based on entire sequence x1, x2, xi, because we have access to the entire sequence. Okay, so we are trying to make a remark of, before we go to the decoder, we are trying to make certain remarks about the encoder. So what encoder have is that it does have access to all of them. Okay, but then we created some positional encoding, but it has access to all of them, but they are sequential nature. So we can add some positional encoding to encode that, and then it goes through this layer normalization, multi-head attentions, and then it has these 6 of these stacked together. So that forms the encoder block for us. Okay. Then for the encoder, it is okay that I have all the entries of the sequence visible at once. Okay, because if I'm going to do translation of English to French or something, then I do have the whole English sentence in hand. Okay, so this is okay. So encoder will have access to all of them, and for the decoder, the decoder's job is to take target input for teacher forcing, and use them to train the decoder to output the next sequence. Okay, so encoder job is to encode, and it does have access to all the tokens in the input sequence, but then decoder job is to take a target input for teacher forcing. Okay, so if you recall the teacher forcing, and use them to train the decoder to output the next sequence. So let us say I'm training a decoder to translate the given sentence into, let us say, some other language like French. Okay, so then it will be done via teacher forcing. So by teacher forcing, it means is that we will let the decoder produce the first word, and then we will check from the correct translated word whether it matches with the correct translations. If it not, that acts like a teacher. So we will say that, okay, you do back propagation, you update the weights because the word that you predicted is not correct one. So that's the teacher forcing that we have seen before, and that's how we are going to train the decoder. Okay, so that's the job of the decoder. So if we continue with the remark, then so for the moment, the multi-head attention decoder, the multi-head attention, the decoder is able to look ahead. Decoder is able to look ahead. So I have not shown you this decoder view yet. So I will use this board now to show you the decoder view, and that will help me explain the third point. So let me draw the decoder now. So let us draw the decoder block. Okay, so let us say we are doing translation. Where can I find a PG area? And then the output is I believe is Hungarian. And then so these are the actual outputs that I want. And the decoder goal will be to take some encoding from here. So we will show what encoding information will be used here. So with the help of that, it will start after inputting the start token, it will start producing the first word, which should be essentially HOL. The second should be TALA, and the third token, and so on. And this is also has some its own subword tokenization, I believe. Okay, so the point here is that decoder has to produce this with this one token after the other. Okay, so this also decoder in the transform model has its own multi-head self-attention. Okay, so this is multi-head self-attention. So this is like encoder, it also has its own multi-head self-attention block. Okay, so we have the positional encoding as well here, because there is a ordering also for this y1, y2, and so on. Anyway, so we have this multi-head self-attention, but the point here is that this multi-head self-attention should not behave in the same way as multi-head attention of the encoder. Okay, so the multi-head self-attention of the encoder has a view of all the entries in the input sequence, but for the decoder we cannot have that, because decoder is supposed to produce one sequence after the other. So it should not see the other sequence in the future. So it should only look at, if it's producing the first word, it's only look at the first word in the sequence, and then it should only look at the previously produced outputs, and based on that it should create attention only among those. Okay, and then if the third input comes, then it should produce only attention between the first three, and it should not see the next ones, because the reason why is that if you allow it to see next one, then the decoder will start cheating, and it will, because it sees the other one. If you build a loss function, and then the loss function, you will do a teacher forcing, and then you will say that after y1 it's y2, and after y2 it's y3. The fact that it was already given access to these translated words, then it will directly take those words during training and make the weights of others completely zero. Basically it will start cheating. It's not learning, it's just that it's relying on the fact that my translated word is already given to me. Okay, but then these translated words are only for you to do the teacher forcing, make the network learn, not to provide as it is. Okay, so that's why we need a concept of masking, in the sense that we mask out the future tokens that are supposed to be produced. Okay, to force the training of the decoder network. Okay, so this is what we are trying to say here. So so to look ahead at the rest of the decoder input, look ahead at the rest of the decoder input. So what did we see here? So for the moment, the multi-head attention decoder is able to look ahead at the rest of the decoder input in the current setup, if we have that. Okay, so as I said, we need to block that. Okay, so we need to block the decoder to future inputs. Okay, we need to block the decoder sees those future inputs. So hence we use something called masked multi-head attention. Okay, so the keyword is masked. Okay, so basically we mask out the future tokens that are coming. Okay, so So let us see how the masking will be done. So if you see this in multi-head attention, if you recall multi-head attention, then we calculate something called attention scores, right? So these attention score is something we are going to mask out. These attention weights we will make it basically lower triangular. So if you make this lower triangular, then if it is calculated with the value pairs, let us say, then those future input, all these will be masked out basically. Okay. So the reason the way we will do it is via creating a attention score which is lower triangular. So let us see how this is. So remember that we create attention score matrix. So like this. Okay. So when we create this self attention, then there is a place where we create these attention weights, right? So these are after the softmax. Okay. And these are for different sequences. So this is for first sequence, this is for second sequence and third sequence. Since we don't want the future sequences to be taken into consideration, so we can create a mask like this, which is like this. Okay. So there is just 1, and these are 0 basically. Okay. So this is, we create a lower triangular matrix which creates a mask for us, and this mask then, and so when so the attention weights that are only below the diagonal basically will be taken into considerations, and remaining ones will be this will correspond to the future ones, and these will be kind of discarded. Okay. So then this gives us a masked attention score. So we can also have visualizations like this, that the attention scores below the diagonal are left as it is, and this we can assign it to be very, let us say, a negative for this. Basically we are not supposed to use those. Okay. So when we are computing the when we are going to use these attention matrices, then we have to make sure that we only use the lower triangular ones. Okay. And those on the upper triangular ones, we make it so negative values that they are not used at all. Okay. So this is called masking, and this has the effect that if we look into the multi-head self-attention block, so let us say we have the multi-head self-attention, and then we have these sequences x1, x2, x3, and then this is the masked multi-head self-attention. Then this is the output that we are going to produce. Let us say, then with the masked self-attention, the output that is being produced by this only looks into this. Okay. So you can explicitly code this in a way that these are not looked at all. Okay. So when you are computing these attention scores, and you can do it at the level of the attention scores, when you reach the attention score, then you can enforce these such that only the low triangular ones are left, because it's like a matrix. We can arrange that. We have seen that. So if we make it low triangular, then it's only looking at the previous one. Okay. So at time step 2, it's only looking at the attention scores that goes with the first 2 sequence. At time step 3, it's only looking at the sequences for attention scores given up to 3. Okay. Beyond that, it's very negative value, so it's useless. Okay. And then similarly, so it will give only attention to this, because these are positive attentions. Okay. So that's how we can create a so-called masked self-attention. So this is to enforce that the teacher forcing basically. Okay. So this is our masked self attention, and then this was a major step in the decoder, and everything else remains more or less the same. And you do similar stabilization of these via this skip connections and so on. So I'm just going to fill this now as the rest. So add skip connection plus layer normalization, and then we have multi-head. This is also a change here, multi-head cross attention. So this is where the output from the decoder is used. So this is the encoder that you have, and this encoder outputs are arranged in a way that they have the key query and values that we have. Okay, so these from there we use the keys and values of the encoder. So multi-head attention, cross attention uses keys, queries, and values data. Okay, so these key, queries, and value data, you take the one that is produced by the encoder. Okay, so so that's, you don't create here the its own keys and values, but take the one that's coming from the encoder. Okay, so that's the idea behind the cross attention. Okay, so everything else is the same, but the keys and values are from the encoder. Okay, and then it goes through so basically again one skip plus layer normalization, and then goes through some feed forward neural network, and then finally again one more layer of skip plus layer normalization, and then finally it goes to produce some softmax or something you will use. So this is softmax, and then from here it produces some y1 hat output, y2 hat output, and yi hat output. Okay, so this is the picture of the decoder, and then here again you have this skip going on like this. It goes here, and then from here it goes here, and then from after skip, before there it goes to here. Okay, so there are these skip connections applied again and again just to maintain that the gradient flows well through this when doing the back propagation. Okay, so this is the overall picture of a decoder. Decoder also is stacked 6 times. Okay, so this is also stacked 6 times. The whole idea behind transformer, I will just review this quickly. So what happens in overall transformer is that you have some source input. So let us say one sentence. This sentence is broken down into tokens. So this could be subword kind of token. So there is the common words are kept separately, but then those words which are not very common, they are created in subwords. They are given some vector representations. In this case is this, and each of these vectors are embedded into, let us say in the original paper, 512 dimensional, and then number of words in the sequence are denoted by I here. And all this go through positional encoding. This positional encoding maintains the ordering of this sequence by using sine and cosines and so on. And then it goes to the encoder block, and this encoder block is stacked 6 times. The output of each of these encoder blocks are same as dimensions as the input. So hence we can stack them one after the other. And then within the encoder block, we have some form of layer normalization, basically normalization of the input data that goes in just to create a data which is good for computing, let's say. And then it goes into multi-head attention. Within multi-head attentions there are like 8 heads. Okay, in the original paper, and then if there are 8 heads, and if it's 512, then each head produces a key query value data, and each of these key query value data is 64, 64, 64. There are 8 of them, so 64 times 8 will be 512, and then they produce these outputs, and then there is a scaled self attention that goes on with key, query, and value for 8 of these heads. And then after doing this, then the final output that we have, we also calculated the formula for the scaled self attentions. Basically it's a softmax of k q transpose times v, okay, something like that. And then the output data remains same dimension as the input data, in this case I by 512, so that output is again I by 512. Then we thought of again doing a layer normalizations just to keep the network stable basically. And then we also have a skip connections here. So this is the modern variant of the encoder block. The way the skip connection is done in the original paper is done in a slightly different way, but this is more stable. So here this input data itself is fed directly into this, along with the output for the multi-head attention. So these are the tricks, neural network tricks that is done. There are skip connections, 2 skip connections here, and then layer normalizations being done, and then the output is being produced. This output is again fed into another encoder block, and this is done 6 times. And once it's done 6 times, after 6th time, this output encoded outputs h1, h2, hi are created. This output is the encoded output. We believe is the very good representation of the input data. Then we go to the decoder block. In the decoder block, let us say we are doing language translations, that we have the English word, where can I find a page area, then we are looking for the translated word in Hungarian, let us say. Then when we are looking into the decoder block, we also have this multi-head self-attention, but then we realize that we cannot have the same multi-head attention like in the encoder block, because if we have that, then the multi-head self-attention will have opportunity to look into all of the vectors, all of the tokens, basically input tokens. But this will defeat the purpose of training the network to translate, because then it will just learn to see the answer directly. Okay, and this is not the idea. We want the network to learn to produce the answer, not to see it directly, because in the answer it's already given what comes next. So that's not a good way to train. So that's why we want a masked variant of the multi-head attention, where after creating the attention score in the masked variant, we mask out the attention that is given to the future sequence tokens in the translated word. Okay, so and this we do it in the form of attention matrix. So basically we give a very negative value for this, and then we retain the whatever value it has seen here. So if it's in first word, then it only gives access to the first one. If it's the third times third, it is going to produce the third word in the sequence, then it has access to the previous two, because it needs to see what was the previous two words produced, and based on that it will learn what to produce the next. Okay, so this way we have a concept of, so this changes to masked attention, multi-head attention. Okay, so this is like masked multi-head attention. So that's the difference from here to here. And then we use the usual neural network tricks, like we add skip connections, layer normalizations, and then we have multi-head cross attention now, compared to what we have in the encoder. So in multi-head cross attention, we take the keys and the values from the encoder block, basically. So in multi-head cross attention, we have these key query values, but now for keys and values we take the one that is produced by the encoder block. Okay, that's why it's called cross attention. So that's how the encoded information is used here. And then we follow with the skip plus layer normalizations, feed forward neural network, and skip again furthermore skip plus layer normalizations. And then we do a 6 of these blocks. 6 times we repeat this, and then finally we have a softmax at the 6th step, and we produce these outputs. Now based on these outputs, we can build a loss function, obviously, and if via teacher forcing, so we have also seen this before, if these words are not matching, if the second word is not matching with the HOL word, okay, then the prediction was very bad, then we go and we do the backprop. So when we do the backprop, neural network has a parameters of the neural network, so that will get updated. Okay, so all this wherever we have the weights in computing, let us say multi-head cross attentions, let us say we have some weights for the query key values, those need to get updated, and so on. And in the later variant, even positional encoding may have learnable parameters to be learned. Okay, in the original paper it's not. So this way it can do backpropagation. It can also go here, and then it can also, because it is possible that the encoder has not produced a good encoded representation, that led to decoder not learning very well. So the gradient can flow, backpropagation can happen here, and this neural network weights will get changed, multi-head attention weights will get changed. Okay, so this way this encoder decoder model can be trained end to end. Okay, so we have another sentence coming from English words, and then it goes through this, and then it produces this, and then again, if the translation is not good, it updates the weights of the neural network like that, and then I will put next sentence again, and then it will. So imagine you have like millions of sentences like that. So at some point it is going to learn how to translate, let us say, an input language to the prescribed output language. So this is how we train transformer networks end to end. So that's what is being used by ChatGPT or GPT-3, which is very popular these days. So I will end this discussion with a very small remarks about ChatGPT and what is the state of the art going on right now. So I will just add few remarks about that, and then close this. We have seen GPT has become very popular, and it can do a lot of things, like it can write poetry, it can write do summarizations, it can solve some maths problems and things like that. And this is what I started with this course. I started with saying that we have GPT and how it's solving some interesting problems. So GPT, and we can say that this is N. So we have seen GPT-3, and by February of this course, February or March, I don't exactly remember, we had GPT-4 also, and when we started it was GPT-3. And this is a very powerful model. It is based on predicting the next word in the sequence, and I can just put some few remarks about this. So this is trained to predict next token. So basically it's trained to predict next word in the sequence. Okay, so but it is done at much larger scale, and it uses sophisticated engineering. So basically one of the sophistication is it uses some reinforcement learning, RLHF, I believe. So reinforcement learning with human feedback. So this is another additional layer in the GPT that if the answers are not very nice, then there is a human feedback also that kind of gives some reward, and then based on that reward the model can go back and again try to become better in predicting. So just to tell you about GPT-3, then it has 45 terabytes of data. So it used 45 terabytes of data collecting from internets, documents, and basically anything that you could get hold of. So it had hundreds of billions of tokens. The model had 175 billion parameters. Okay, these are very huge numbers. It has 96 blocks. So we are talking about 6 of the encoder blocks, but the GPT-3 itself has 96 blocks. They have not told us anything about GPT-4 yet, so the data is not very really told about GPT-4. But if you look into GPT-3 itself, so it has 96 blocks, okay, encoder and decoder blocks with 96 attention heads. Okay, so these are the numbers they have thought of about due to scalability reasons or whatever they could, but these are 96 blocks. It's a huge, and then 96 attention heads. We had only 8 attention heads. They went with 96 attention heads, and then 3.2 million batch size 3.2 billion, and then 2048 token context size. Okay, so in our case it was 512 in the original one, the token sizes, the X size, but they took 2048 as a embedding dimension size. And obviously the applications of the ChatGPT are many. By now you know that. So it can be used to write poetry, help with coding. So it can do some initial codings. You can say that write a Python code for something. Okay, write a SQL code. Okay, write HTML code for a website. Okay, so it can do many things. Write a summary of certain articles. So it can solve puzzles. So basically the applications are basically endless. Okay, so in GPT-2, in GPT N models, it is a decoder only model. Okay, so basically what happens is that they have a pre-trained transformers. So that's trained on many data, and then they take this. Okay, and then once they have this trained ones, it's a next word prediction type model. So then you can ask a question. So that becomes your couple of words in the sequence, and then let it predict the next set of words in the sequence. So then the network has been trained on so many data like that it sees some words, and then it knows how to predict the next set of words. So this is how. So it's a decoder only model. There are also other variants of pre-trained transformer like BERT. So this I believe BERT is encoder only model, and then there are many variants. There are encoder decoder model as well. So there are many variants of this, and this is the. So as I said, there is further software engineering in the form of reinforcement learning with human feedback. I'm not going to cover that for the moment, but that makes these models even better. So with this, I will stop my lecture, and thanks for your attention.